Hi. Hi. So let's talk about supervised fine-tuning in the context of LLMs. Supervised fine-tuning is also more commonly known as SFT, supervised fine-tuning. So it's the stage one, right? Once we have done the pre-training, once we have taught the large language model to just output the next token, then we want to give it some additional information. We want it to do specific things. We want it to, give out an answer when we ask it a question and not answer the same question with another question. Not just do completion, but actually follow instruction. So we want to teach the model the format of a conversation. And to do that, what do? We give it this prompt response pairs. Yeah. And we still minimize the same loss. I'm going to show you in the next slide. And this is an actual data set from Alpaca. So if you go to this Stanford Alpaca GitHub domain, the GitHub project, and if you look at the JSON, the dataset.json, you will find a file like this. And let's look at it closely, right? So this is the instruction. This is the instruction that we want the LLM to follow. What is the instruction? Convert from Celsius to Fahrenheit. So this is essentially the prompt. And then there is an input. So the input is essentially the context. And what is the context? Temperature in Celsius 15. And this is what we want the output to be. But again, I want to emphasize that even though we have this instruction / prompt, context, output pairs, we still only minimize the word level losses, right? So what we want is we still expect the same words to come out like here, and then for every word, we simply minimize the cross-entropy error. And more on that in next slide, but let's look at maybe one more example. So here, what is our prompt? The prompt is arrange the given numbers in ascending order. And what are the numbers? It's 24083, and as output, so this is your context, the 24083, and output we want 02348. The answer, the list actually sorted in ascending order. So how does the training work? Well, there is a transformer, and what does a transformer do? The transformer simply enhances your embedding, right? Given an embedding, so let's say this is our transformer block, we have a bunch of tokens coming in, so these are the embeddings of the tokens, and then as output we just get the same tokens but different embeddings, right? These are the enhanced or the revised embeddings of the same tokens. And now we then put it in a linear head, and then the softmax, and then the entire vocabulary, right? So if you remember, we spoke about this linear head. So this then, this may be 4192, and then so this may be one row and 4192 columns, and then we have a linear head which goes from say 4192 to 50k. Yeah, and this projects this embedding into the vocabulary space, from where we can then know exactly what word it is, because from an embedding we are not able to tell, but then we can project it into the vocabulary, and then we can tell what word it actually is. And what we do is, if it is the correct word, if it is in the same sequence, if it's the correct word, we don't minimize. If it's the wrong word, we minimize the cross-entropy error. Yeah, the negative log of the correct class. And we do this kind of a masking. So the prompt, we don't want to penalize it if it does not kind of output the prompt right, because prompt is just an input. What we want to minimize is the response, right? The output. So we only want to do it for the output. So for the prompt and the context, we don't want to minimize the loss. So what we do, we take the negative log of the correct class, negative log of the correct class, add all of them up, and then minimize this. And that's all that there is in SFT, in supervised fine tuning. So only compute loss on the response tokens, not the prompt. Now let's look at SFT in code, and we will walk over this notebook in a bit, but it is essentially a tool calling example where we teach an LLM to call tools. Tools can be like web search, send email, read text, etc. And what we have is this SFT trainer, and we then have, the before and after comparison. So before, if you ask it a question like what's the distance between New York and LA, it gives a textual answer. It says the distance is about 2870 miles. It's a long cross country trip, and it's a plain text response based on the pre-training, right? But after the tool calling SFT step, what it is able to do is it is able to say what is the difference between NY and LA, and it calls this tool and it calculates the distance between origin and destination, and it has those begin tool call and end tool call tags. And if you look at code, well, we simply import these from SFT trainer and SFT config, and we are doing fine tuning this Qwen 2.5 1.5 billion instruction model. So it is already trained on instruction, and this is why when we ask it a question such as this, it answers a proper text. It doesn't continue to just autocomplete that sentence. And then we'll look at something called as LoRa later, but let's not worry about it. And here we simply have to, because it's like so highly abstracted, we just need to give it the right configuration. We just need to say, okay, what is the output directory? What is the number of, train epochs? You have to, some other these hyperparameters. And then in the SFT trainer, we just have to give it the model, which is your Qwen 2.5 model. This 1.5b instruct model. We give it arguments, we give it the train data set, and we have to then also give it the eval data set, and it takes about 2.4 minutes on the GPU to train on this. And I'll show you the data set in a bit, but this is all that there is when you want to do SFT. But there are other stages after SFT, for example reinforcement based fine tunings, and we'll talk about that. But why do we need to use reinforcement learning? Why is SFT not enough? And the answer is that there may be many valid answers, but SFT will penalize all but one. Meaning, your answer could be his name is Arjun. Arjun is his name, right? Both are valid answers. Arjun is his name, and his name is, let's say, Arjun, right? But now cross-entropy doesn't know this. Cross-entropy only knows that, let's say, we have ground truth this, but it answers this, right? And in ground truth, Arjun is here, and it just looks at, okay, did it output Arjun or not? It outputted his, so it will compute the loss based on that. Similarly for this and this. So even though there are multiple ways of saying the right thing, it only knows one thing to be right, because that is what we're computing the loss against. So this is bad for the model, right? Because even if it gives us the right answer, we are kind of saying, no, you did something wrong, and you penalize it. So the model gets confused. And this is one of the major shortcomings of SFT. And in the next steps, we will see how to overcome this.